I'm Mark Miller of Agoric. My talk today is Stopping Exfiltration. This is a talk that I just gave at the end of May TC39 meeting. The TC39 is the committee that standardizes the JavaScript language, the ECMAScript committee. At the time I gave it, the slides are posted, but the talk itself was not recorded. The slides, when I gave it, we had tremendous audiovisual problems. So giving the talk today, recorded, is solving several problems. It's recording the actual content of the talk, as well as making the talk as it was intended to be given available to all those who should have seen it in the first place. The web has many exfiltration issues, some of which have been long known, some of which are news, some of which are not widely known. The issue of exfiltration is when information that should have been private is leaked to an adversary elsewhere, often by virtue of code that is able to obtain the secrets in ways that are outside the intentions of those who hold the secrets. So the main old form of exfiltration that's well known is covert channels and side channels.
Oh, I thought the traditional way of exfiltrating was to write it on a tape or a thumb drive and carry it out.
So that's the model where the attacker is a person within a building. In this case, the model is the attacker is a program within a computer. And so the details are different, but the structure is related.
Okay. So in a covert or side channel attack, you have code that is holding a secret that is computing using the secret in ways where the timing of the computation varies depending on the content of the secret. So an adversary code running on the same machine at the same time, by observing timing differences, can often gain information about the secret and then leak it out. The severity of covert channels and side channels turns out to be much worse than most people were expecting with the discovery of the meltdown and Spectre attacks and the various variants of them. It turns out that the susceptibility of modern CPUs to leaking information through covert channels and side channels was just much more severe than people were expecting. And then the channels over which information can be leaked can be divided into covert channels and side channels on the one hand and overt channels on the other hand. Overt is a communications channel which is according to the semantics of the platform in question, whereas covert and side channels are making use of behavior of the platform that is not part of the specification of the platform. It's sort of making use of accidental leakage that happens to be a property of the implementation rather than the specified behavior. So on overt channels, we've always known that classic computer insecurity in the architecture can enable, by sort of direct attack, the leakage of secrets. And there's some news about the actual occurrence of such attacks that had been predicted for a long time, but the actual occurrences of them are also surprisingly prevalent and severe. So I want to get into all of those. And then after explaining sort of the modern web exfiltration problem, I'm then going to talk about what to do about it.
Can you specify the distinction between a covert and a side channel?
Yes, thank you. So covert covert channels and side channels are both non-overt channels. The difference between them is only one of intention. A side channel is when the computation that is leaking the secret does not intend to leak the secret, that the secret is leaking as an innocent consequence of simply what the secret holder is doing for its own purposes. A covert channel is when the entity that's holding the secret intends to leak it. They are not supposed to be able to leak it, but they find a means to leak it anyway. The classic metaphor for all this is actually still a very nice metaphor. Covert channels are often described in terms of wall banging. You have, let's say, two prisoners in a jail that are not supposed to be able to communicate, that are in separate cells, but one of them bangs on the wall, and the other one is able to hear the banging, and maybe the banging is in Morse code or whatever, hear the banging and decipher it and receive the messages. The metaphor of the sound channel of hearing is very nice, whereas the metaphor for sight for overt channels is nice. And with sound for the non-overt channels, it's also the case that somebody who's not intending to leak a secret, but just doing things in ways that create sound might leak information to someone who can hear the sound that they're generating. And then the nice thing about sound versus sight as metaphors, I'll keep trying to use sound and sight terminology when referring to these channels, is that sound goes around corners in ways that are not easy to control, whereas sight has this line of sight restriction, so it's sort of easily blocked, and it's easy to know when you've blocked it.
Mark, this is Jazz. I've always liked this distinction that is made in covert channels between side channels. The distinction that you make based on intention is great. It has always been interesting to me that overt channels are not divided that way, even though they are intention-based distinctions, even on the overt channel. And the explicit example is just because programmers don't understand, let's say, cookie sharing mechanisms, there is an overt channel that occurs via cookies, for example, but the programmer's intention was not to leak this information. Do you think that that distinction in overt channels is worth making, or is that
I do, and sometimes I refer to I use the term subliminal channels, borrowed from the cryptographic use of the terminology, for a leakage of a secret as encoded in overt messages, such that the overt messages are delivered inadvertently transmitting the encoding of a secret. So for example, I'm sending you a JPEG, but I encode in the bits of the JPEG a steganographic secret that's really intended for something else, someone else. You receive the JPEG and innocently post it, enabling somebody to decode the steganographic secret. The steganographic encoding and the transmission of the JPEG is all overt, but your transmitting of the message encoded on it is not part of your intention, it's part of my intention in encoding it. So those intentional differences on overt channels are all very interesting. There's a whole, the whole taxonomy you can create there. In this talk, I'm not going to be...
It's overt, covert, and the other parts of the taxonomy were...
So there's overt versus non-overt.
Yeah.
On the non-overt side, there's an intentionality difference between covert and side. On the overt side, there is an intentionality difference between subliminal and
Overt.
And overt.
Overt, intentional.
Overt.
No, because subliminal is still overt.
Oh, okay.
So
Subliminal and the rest of overt. Subliminal and intentional.
I think this terminology needs some work, but
yeah.
I'm gonna need a graphical depiction.
Yeah, exactly. A tree taxonomy would be great.
And you can transmit to that to me either overtly or covertly, as far as I'm concerned.
So with regard to this talk, I'm only going to be focusing on the distinctions that don't have much to do with intention. So really, the overt versus non-overt is the main issue there. Oh, actually, no. Let me elaborate that. Actually, I'm going to be talking about where the leaker is not intending to leak. So in the case of the non-overt channels, I'm focusing on the side channels rather than the covert channels. And likewise, on the overt channels, I'm not focusing on subliminal channels.
So those are collectively inadvertent.
Right. So the overt theft is where the holder of the secret doesn't intend to leak it, but the one who gains the secret, who's the attacker, is gaining the secret from someone who did not intend to leak it. And okay. And part of the message of the attacks that I'm going through is that there's a standard piece of advice that is often given, especially by some prominent browser makers. But you actually hear this a lot. You hear, which is the only security boundaries supported by the web are the origin boundaries. And therefore, the only boundaries that you should use as security boundaries are the origin boundaries, and the result is that all code that you load into the same origin must be completely mutually trusted to each other, because it's all fully vulnerable to each other, and that therefore people should fully vet all code that they load into an origin that contains anything that's of value to them.
So how does CORS play into that?
CORS itself,
I mean, theoretically, you're doing it consciously, but it just seems like a lot more rope to hang yourself with.
So CORS itself is a small part of the overall problem that I'm trying to highlight here, which is, in general, wherever you get the third-party code from, whether you're getting it from another origin or not,
right.
Even if you're getting all the code as served by a host on your own origin, any substantial website is linking in tremendous amounts of code that it has no basis to trust, that it's written by
unknown parties.
Written by other parties, often even if it's written by people in their own organization. It's not written by security experts in their own organization. Even if it's not written to be malicious, it might be exploitable in such a way that it can be exploited by someone else, so that once subverted, it becomes as if malicious. So the main problem here is that this advice implies that the way to use the web securely is only to run code in your origin that you have fully vetted, that you have come to understand is code that is not going to attack you, that you can trust to operate securely.
You are glossing over the fact that we've learned over time that bugs are attack possibilities, and so just claiming that it's malicious stuff that we're worried about leaves too much out.
That's right. That's right.
When you have a substantial body of code that you're trusting that you can't have written all of yourself, or that you don't trust yourself to have written all perfectly, then it's all attackable in some way. And if you're vulnerable to it, then it's worth it.
Mm-hmm. Yeah. So code which is subvertible because of a bug, once subverted, acts as an attacker, even though the code itself that got subverted might not have been coded intending for it to be the attacker.
Yes, intention is a very weak trust
right.
metric.
Yeah, so people keep talking about trusted code and untrusted code and saying things like only run trusted code within your origin. And my response to that is, I don't trust the code I wrote yesterday.
Or I'm going to write tomorrow.
Yeah, that the real issue is robust composition. The issue is composing separate pieces of code, each of whom is fallible, each of whom has some probability of being erroneous, and having frameworks of composition such that you can often realize the cooperative benefit that is the purpose why you're composing the code. So you get maximize the benefits when things go right, but at the same time, minimize the risks from destructive interference. And when the destructive interference is intentional, we call those attacks and study them in computer security. When the destructive interference is accidental, we call them bugs and study them in software engineering. And my main message in a lot of this is we shouldn't care so much about whether the destructive interference is accidental or intentional. The same mechanisms are largely useful for dealing with both issues. And if you write software and you create composition frameworks which are robust against intentional interference, if you try to be robust against intentional interference, you will often succeed better at also being robust against accidental interference.
Reliability and security are two sides of the same coin.
Yeah. And this advice that you hear a lot about origin boundaries, what it implies as the recommended practice is so unrealistic that it really should be understood as like the position of the car companies saying, oh, the Pinto blew up. Well, that's just operator error. You shouldn't have crashed it. That's a shedding liability strategy as opposed to a strategy of trying to protect the users. And over time, cars became became more forgiving of realistic user behavior. It's not that it's now impossible to crash a car or even impossible to crash a car accidentally, but cars do more and more to be more forgiving of realistic driving behavior, so that it better helps drivers by engaging in best practices avoid dangers. Although not perfectly. Even with best practices, sometimes cars will crash. So we should also seek to build technology that over time becomes more forgiving of realistic behavior. Protect our users rather than seeking only to shed liability. So the talk will contain a bunch of quotes from various papers. There's a slide at the end of the talk where I actually have the links and the citations to all the sources of these quotations. But as I go through the talk, I'm not going to go through where they came from or go into detail on the citations. But there's a research paper that was written before Meltdown Inspector, is not making use of Meltdown Inspector, is just making use of cache timing vulnerabilities in the browser, and finding that that cryptographic code that was written to do constant time algorithms, meaning algorithms whose timing does not reveal the keys, that the timing of the algorithm should be the same irrespective of what the bits of the keys are that the cryptography is using, what they found was that they were able by in the browser from JavaScript to make use of cache timing attacks to gain the cryptographic key information from those libraries. And that is the best case for avoiding leakage of non-overt channels is when the algorithm is coded by the good guys not to leak, and you're looking at the highest value secrets, which are therefore the ones you're doing the most effort to protect, which are the cryptographic keys. So even there, and even without Meltdown and Spectre, we were already not succeeding at preventing leakage. The Frozen Realms proposal, which is before the committee, said back in 2017, I wrote before I knew about Meltdown and Spectre, I made the observation that computation that is limited to a certain, essentially limited to determinism, there's some qualifiers in there that we can elide for now unless there's questions. But basically computation that's limited to deterministic computation where it can't get dynamic, it can't read dynamic forms of non-determinism, and in particular, it cannot sense the duration of time. Does not have a timing channel available to it, cannot sense information leaked over covert channels. So going back to the hearing analogy, on the one hand, you have maybe a prisoner that's intentionally banging on a wall, or maybe just an innocent party that's going about their business and making noise from that. If you could hear it, the information would leak. But computation that's restricted such that it cannot execute non-deterministically and cannot sense the duration of time is basically deaf to those audio channels. It can't hear it. You can't prevent, on the one hand, the creation of the dangerous sound, but you can prevent particular adversaries that you're in a position to deny a timing channel. You can prevent them from hearing what is on those audio channels.
So are you saying that all covert and side channels only use timing?
No, I'm saying they only use non-determinism.
Mm.
And the primary form of non-determinism that these things use are timing.
Right.
Timing is the thing that people would like to not think about in computer science.
What about using control flow? If you end up here, I know it's a 1. If you end up there, I know it's a 0.
How do you know where I've ended up? How do you know? I mean, the thing is,
the same little trick that we discovered, after the fact of discovering timing. Maybe there's some way in the future to.
Right. So
Inspector kind of does that, right? They put a cache miss on a branch mispredict.
Right. Yeah. So this is the issue about, this is exactly where the boundary between overt and non-overt is relevant. Is if you have a way to read the location of my program counter that is given to you by the specification of the platform, such that any possible conforming implementation of the platform necessarily makes the information available to you in a specific way, in a standardized way, then it's an overt channel. And the fact that maybe I didn't intend my program counter to leak the information.
I don't even need all the program counter. I can just say if you end up somewhere in this 1 megabyte versus this 1 megabyte.
But the question is, the question is what is the means by which you're gaining the information? So let me give you a concrete example of an overt but unintentional leakage of control flow information that I was guilty of, which is in the version of E that we took into the DARPA browser security review back in 2003 or so. Dean Tribble and David Wagner were our adversaries, our adversarial reviewers. One of the things they spotted is that when an exception was thrown, the stack trace from which the exception was thrown was made visible to whoever caught the exception. And they observed, and it's recorded in the Docker Browser Security Review, which is public on the web, that creates a danger that if you call into something in which the internal stack of the thing grows in a data-dependent way, the stack that's revealed is only revealing a stack of program counters. It's purposely not revealing any data.
But it's also revealing control flow, right?
But
that's the call graph, right?
Yes.
It's revealing the stack of essentially the stack of program locations in the stack of functions being called. So if I call into something, then let's say I do it in a way that causes that provokes an exception, and then the exception gets thrown and I catch it. It's quite possible that by taking a look at the call stack, I can gain data-dependent information, and then we fixed E so that it would not leak that. Likewise, there's a proposal before the committee of standardizing the revelation of error stacks in JavaScript, and that's very carefully crafted so that you can have a conforming JavaScript implementation that does not leak the stack trace information to unprivileged catchers.
Right, and I may not even need the program counter. If I can somehow know that on the left side of the branch you execute a floating point multiply, but on the right side you don't. I just need to, detect some.
That's right.
I don't need the PC itself necessarily.
You're counting on timing?
No, I'm counting on, did you execute a floating point multiply or not?
But the question is, how do you know whether I executed?
Some other implementation-specific side channel.
Yeah, exactly.
Right, but the question is, if it's implementation-specific, then it's a side channel. If it's guaranteed by the semantics of the platform, like the error stack trace, then it's overt but unintentional.
And if you, the attacker, are limited to functionality that is deterministic, then it's hard to see how you can probe the path taken by code that you're calling.
Right.
You can only react to, because that by definition is not deterministic.
Right. Right. So it might be deterministic that you can ask and get an answer. That's the determinism.
So in summary, for Spectre, like comedy, timing is everything?
Yeah.
What I was thinking about, Martin, is that if I can ask what your program counter is, the value of the program counter is probably non-deterministic.
Non-deterministic in what sense?
The bits are not determined by the previous, by my inputs and what I've done with them.
In the bug that he was just talking about, it was deterministic. You provide the data, you make the call. The exception is thrown depending on the data that you provided. So it is deterministic.
Yeah. Yeah. So in any case, so this one shows that even without Meltdown and Spectre and only looking at timing channels and looking at the best case defense against these things, we were already in a much worse situation than we thought we were in. And then furthermore, the Frozen Realms work and the work in the Frozen Realms, that tradition of work, a lot of the object capability language work was very explicitly only making strong claims about avoiding covert and side channels by imposing determinism. It was assuming that information was leaking over non-overt channels to anyone that could sense non-determinism, in particular sense the duration of time. And therefore, we were only making strong claims about integrity, which is not threatened by any of this, and claims of confidentiality only with regard to the limitation of determinism. So I wrote that text back in 2017 before I knew about Meltdown and Spectre. With all of these surprising revelations of Meltdown and Spectre and all the variants of it, those claims and that statement remains just as true as it ever was. So now let's talk about overt theft. there is a platform that has become very important out there in the world, in the sense that many widespread apps are built using this platform. It's called Electron. And Electron is essentially the grafting together of the Node server-side JavaScript engine that has, where Node is basically providing access to the JavaScript code of things like the file system. It's kind of this sort of, you can think of it as a JavaScript abstraction of a sort of universal POSIX-like local operating system services. Grafting of that server-side technology with the browser-side technology of things like Blink or WebKit, essentially the Chrome or Safari browser-side.
Just access to the DOM.
With its own DOM and rendering engine.
So this is running outside a browser, right? This is Node with a nice render.
Yeah, it's basically the browser mechanism and the Node server mechanism grafted together as a separate platform. It's a platform outside of the browser. You can't download it into a browser as the content of a web page. It's a separate thing. But many things that people download and install as apps are actually written on top of Electron. It becomes a very, very nice framework for building apps, and it itself is a nice portable framework, so you can build apps for many platforms by just building them in Electron.
So this is your classic example of a big library that you can practically examine for security.
And that's before you even load any code into it.
So there have been discovered various kinds of vulnerabilities in Electron that have to do with the fact that the JavaScript code, the overall JavaScript code running on Electron, is pulling in all sorts of JavaScript libraries that might have originally been written with the expectation that they're only being run on the server side in Node on the one hand, or only being run on the browser on the other hand. Since they're compatible with either or both, they are often pulled into Electron. And in Electron, the normal way you build an application is all of these things run linked together in one security boundary. Brendan, from a tweet from Brendan Ike, points out that with this mixing of code, the libraries could, for example, these unvetted libraries could, for example, replace function.prototype.apply, poison the primordials, corrupt the system in a way that it intends, and then having corrupted the system that all other code within the application runs in, it can now exfiltrate data and do worse things. And that, as Brendan points out in this tweet, this problem is sufficiently severe that Microsoft at one point was seriously considering banning all apps written on the Electron platform, banning them from the Windows 10 store. So these are serious issues. And the POLA that Brendan refers to is the principle of least authority. And Brendan's pointing out that the reason why these vulnerabilities are a problem is that each of these things, each of these different libraries being brought together and linked together in this origin are not being limited to POLA, are being given vastly more, each one is being given vastly more authority than it needs to do the legitimate job that was the purpose why it's being linked in. And what we have found from systems engineered to support POLA is that when you actually give libraries only the authority they need to do their legitimate job, what we find is that most code actually needs very little authority to do its legitimate job. There's still some code that needs a lot of authority, and that's where you have a lot of risk. But now your vetting problem, the economics of the vetting, get tremendously narrowed down if you can just say, for most code, it's just not given the authority needed to endanger very much. Now you can focus your vetting efforts.
Does Brendan have any proposals for his Pola, either JavaScript-based or Brave
Yeah.
specific?
So let me actually just go forward to another quote by Brendan. Yeah. Brendan tweets, in 2012, I asked, why not boundaries? It's time. Better isolation, OCAP membranes, reduce attack surface. So Brendan is specifically calling attention to the object capability work. And in that tweet, he cites a talk he gave in 2012 that was referring to SES and such work on doing object capabilities in JavaScript. So Brendan has always been very, very supportive.
He understands the problem and how the solution might address it.
That's right. Okay. And then there's been this recent series of research papers from a group at Princeton University, which is the No Boundaries series. And I link to that in the page of links at the end of the talk. I very much recommend this entire series. What they found was they started looking for what are the actual leakages that we see? What are the actual things that look like they might be attacks due to this linking together of code from third-party libraries? And at the Princeton researchers, and they found lots of incidents with regard to one particular form of attack. They found 8,000 cases that look like they are instances of this attack on prominent websites. They're only looking at prominent websites of like major corporations, and their summary of what they conclude, looking at the nature of the attacks and looking at the nature of the vulnerabilities that invited the attacks, is that this unrealistic advice from the browser makers is actually not advice anybody can practice or even advice anybody understands that they should practice. To just quote from the Princeton paper, third-party trackers, website, the important part, website operators, by which they mean authors of prominent websites that are then deployed, website operators are in the dark about privacy violations by third-party scripts. They link in these third-party scripts, not understanding the risks, not protecting themselves from the risks. And part of the reason is that that there is no practical way for them to do that protection. Yes.
But these are LinkedIn scripts as opposed to scripts from other origins, like, for example, an ad.
Whether these are not ads. These are things that were linked in.
Yeah.
I don't know whether they were fetched from another origin or not. I think in this case they actually were fetched from another origin. But it largely doesn't matter. Sometimes when you're using a third-party code, sometimes you fetch it from the third-party origin, but it still executes in your origin.
Right.
Sometimes you just copy the code and serve it from your own host, so you're fetching it from your own origin. But in both cases, it was written by a third party. And in both cases, even though it's running on your origin, it can communicate back to anybody else on the web that it wants to.
Mm-hmm.
The web does not. The security measures of the web, bizarrely, like CORS that you're mentioning, doesn't protect writing data. It protects reading the response to the write. So no matter what your CORS restrictions, you can still send data to any origin you want. You just can't get a response back from origins that don't want you to read the response.
Really? I can XHR to
You can do a get with query parameters.
food.com,
Yeah.
even though I came from bar.com?
The XHR will be sent.
Really?
If the response does not have the CORS allow origin header coming back, meaning it's not intending, the response is not one that it intends the requester to read, then the requester is prevented from reading it.
But your message still got delivered.
But the message still got
I didn't realize
delivered.
that. I thought it would trap
Or just
ASHR.
add an image tag with query parameters if you're choosing.
Yeah.
Or the URL will make it, the path will make it to the file.
Mark,
Yeah.
can I make a comment here?
Yeah.
Actually,
Jazz, go ahead.
pressing, but I'm going to be pedantic about the particulars. The web does provide a mechanism that prevents writing as well, and that's the content security policy that does give you the ability, a very coarse ability, to say to where information can get sent.
True. Okay.
And the second is, even when I was reading this particular, the No Boundary series, so this sentiment is actually not checkable by Princeton based on code. The fact that operators in the dark about privacy violation is not you can determine by looking at the code itself.
Jazz, let me say, your audio is being very distorted. Jazz, your audio is very distorted. So if you can improve your microphone situation, that would be appreciated. And in either case, if you can speak a little bit slower, what you're saying will be more legible.
Let me try that. So website operators are in the dark about privacy violations is a determination that you cannot make by reading the code of the site. Intention.
Sorry, we lost your sentence, Jazz.
These privacy violations anyways.
We missed the middle of the sentence. Start from intentions.
It's a covert channel.
So the intention is a very important part of checking of the statement made by Princeton, and it is not something that can be determined by looking at code.
It can't be. Yeah, I mean, yeah, that's all true. But you know, the Princeton researchers, in looking at particular examples and in particular cases, talking to the people involved and getting a sense of how these mistakes were made. I think come up with very reasonable judgments and explanations that ring more true about how most of this composition was happening by accident rather than intentional.
So I have a question about the Electron issues. So my understanding here is that none of the code was malicious, and yet there was a vulnerability due to past primordials. I'm just curious, what did that look like? What did that look like? What were they trying to do that they failed at?
So I do not know. Okay. I don't know much about the Electron stuff in any detail. What I saw was that it was recent news with big impact, okay. And that I knew enough to know that it's an example of the overt theft vulnerability that was causing the impact.
The thing that I remember reading said that the front end code can usually ask the back end code to do whatever it wants. It can kind of make a required statement. It can pull in an arbitrary back end library, get a proxy to it. There was a way that was supposed to be turned off, and part of the attack was that there was a sneaky way for the front end code to turn that back on again. So that compromise of JavaScript on the front end code could get access to the entire backend.
Okay, so there's still malicious. It's not like it's a malicious data bootstraps itself into being cut. There's
an injection attack against the front end code would be successful in taking over the whole backend. Opposed to merely the
that's slightly less subtle than I was expecting.
There's just so many opportunities to attack things. We don't need to be subtle now.
Okay. So the Princeton No Boundary series gives an example of exfiltrating data from Facebook, where the third-party tracker was exfiltrating data that it was using access to data that Facebook explicitly granted it. So once again, this is a leak through an overt channel. Facebook did not intend to enable the tracker to exfiltrate illegitimate data, but it enabled the tracker to do that.
How did the tracker get on inside the browser?
The tracker was legitimately loaded, but was not supposed to be in a position to obtain and leak the data, but was nevertheless given access explicitly that enabled it to do
Could
that.
be described as Trojan horse programming in the library that was included?
Yeah, in this case, I don't know. I don't know if the tracker was running in a separate frame or not. I suspect the tracker was running in a separate frame, maybe in this case with a separate origin. So it's not an example of the library vulnerability. It is an example of lack of POLA leading to vulnerabilities of the overt theft form.
So does this
using
login with
overt channels.
Facebook block? Was that delivered by Facebook? Or is this, I'm not in Facebook yet, I'm, somewhere else in there.
Well, it says the trackers waited for users to log in. So it looks like the
It was
user
already there.
the users are logging in intentionally, and the third-party code is running in a place.
That's what I'm getting at is Facebook has not loaded anything yet.
Well, this is not log in to Facebook. It's log in with Facebook. So
Right.
this is open ID.
Right. That's right. Thank you.
So this is not Facebook screwing up. They
This
haven't
is-
delivered anything yet. You're waiting to log in.
Right. This is Facebook. You know how when you go to many websites and it asks you to log in,
Right.
one of the options is log in with Facebook.
Right.
That's the interaction here.
Right.
Okay.
And that's sufficient to give the code their access to Facebook data.
Yes.
That's
It was not
surprise.
supposed to be sufficient,
Yeah.
but it turned out to be sufficient, and it's sufficient using only overt channels.
Right.
So the problem is not timing or non-determinism. The problem is lack of POLA. The problem is that it was simply explicitly given access that should not have been given.
And if they were using a POLA system, then somebody would have had to explicitly write the code and say, oh, wait, maybe this is the wrong piece of authority to give at this point.
Right. So the Princeton No Boundary series goes on to observe 8,000 sites using a particular third-party kind of service called a session replay script that's for analytics, and took a look at what these session replay scripts were doing on various sites. And they give the example of Walgreens.com as one example of this thing that they found many instances of, where the information sent to the third party for analytics tracking purposes included the prescription data of Walgreens customers being leaked to a third party where there was no contractual arrangement in place that authorized the third party to get private customer medical data. So that was directly a HIPAA violation. Yeah.
I want to respond to Chris's comment about enforcing POLA. All too often, OAuth is a good platform for enforcing POLA at arbitrarily fine granularity. And the most common implementations are very coarse-grained. So even though it's enforcing POLA, it's not being used properly.
Okay.
Another one they found.
That's what you can do with capabilities of any variety.
Yes.
Yeah. Another one they found that's an instance of the same form of bug is that there's a third-party analytics site called Full Story that is used in academia for purposes of supporting various kinds of legitimate academic interaction with students. And what they found was that the information being exfiltrated to this third-party analytics site included student names and emails, student grades, instructor comments on students, none of which were in any sense legitimate by the contractual arrangements between the university and the third-party tracking site. This is a violation of a different set of privacy regs, FERPA. And then the Princeton researchers, having discovered this in other academic sites, took a look at their own site and found that they were doing this too. So this is Princeton's own information security course was one of the website authors that was constructed without taking adequate account of this particular form of danger, I think helping to corroborate the idea that the standard recommendation is just unrealistically hard that even academic information security courses failed to follow it.
So do the researchers say or imply that the third-party data gathering sites were intentionally exfiltrating data they shouldn't have had access to, or were they accidentally including things in URL parameters and other things that they weren't noticing were PII?
As far as I know, nothing that the Princeton researchers found indicates that the third-party receivers of this data were maliciously gathering it. The exfiltration could all be accidental. It's always important to remember when you see one of these things that if you intend to exfiltrate, you want deniability. So the lack of apparent intentionality is
it looks the fact that it was so blatant argues that it wasn't intentional.
And it's interesting that ordinary bugs look like this.
Right. So there's plenty of opportunity, right? I mean, in the case where all this data leaks through common bugs, there's plenty of opportunity to maliciously write code that gets the data and looks like it's just practicing those bugs. So that doesn't accuse any of the particular receivers here of anything malicious. It's just that what they're observing is, even if there's no malice on the part of the receivers, the fact that the sites were sending the data to those receivers and is itself a violation of the privacy properties that those sites were obligated to uphold. And they certainly, the privacy properties they intended to uphold.
Yeah, I got to say, even if you ignore the law here, this is stuff that they probably didn't want to do.
That's right. And in fact, when the Princeton researchers go to them and point this out, they fix it. So okay. So I already mentioned this quote from Brendan. I also found that in the Twitter threads that I looked at that were about this, that there is a political challenge for TC39 here, which is Brendan tweeted with regard to these problems and the proposed boundary solutions that Brendan has in mind. If Apple, Brave, and Mozilla allied in W3C, we could move the needle. Little Dan, which is Dan Ehrenberger, replied on the same thread. I prefer this plan to working through the WC3C to provide a web-wide solution to building OCAPs and TC39 alone. Well, I
noticed he left out Chrome.
I will avoid commenting on that.
Okay. So what? I mean, it's a competitive market, right? Why can't Brave do it first?
So anybody can do it. The issue
then,
is
when someone realizes, oh, this actually stopped a real attack, and
So
learn from other people's success.
The issue of how one proceeds, in the absence of general consensus, is tricky and sort of a interesting and complicated political game. And since I want the overall effort to succeed, I wish that luck. But better would be to actually gain consensus. And in particular, I wanted to take these statements as a challenge for TC39 to rise to the occasion and in fact solve it in TC39 alone, because it's fundamentally a JavaScript problem, not a browser problem.
Yes, well, not to say I am aware of all of the factors here, but it occurs, I suspect that my model, someone saying that says that they are thinking of, they're thinking of a web platform technology, not, or a protocol, not, fundamental paradigms and, patterns, supporting patterns everywhere. They're thinking of something heavier weight than capabilities are supposed to be. I mean, that's just what I'm not at all familiar with Little Dan's views. I'm just saying that's what I would assume from someone, if someone says that thing.
Okay, so So I've interacted a lot with both of these people, and I have to say that I agree that I'm not confident about what in particular little Dan had in mind. However, I am confident, including by explicitly what Brendan says earlier in the thread, as well as many interactions with Brendan, that Brendan does have in mind OCAP language support in JavaScript. He might have other things in mind as well, probably, but he certainly has that in mind. And that part can be solved in TC39 alone. Okay.
In fact, that's the right place to solve it.
Yes. So now let's take a look at the...
Let me just come back to that 1 second.
Yeah.
With WASM, is that going to be true?
Yes.
Okay.
WASM itself is already, as specified, has object capability safety properties. Interesting interaction that happened at one of the WASM standards meetings. There was a 2-day meeting. On the first day, I pointed out that WASM has these safety properties and proposed something that would build on the safety properties. Other people in the meeting were sort of surprised to find out that WASM had these safety properties, objected that, well, maybe we'll evolve WASM in such a way as we lose the safety properties. So I propose we make the safety properties normative, which there was an upvote on. Nobody objected to that. Then the second day of that standards meeting, Andreas Rosberg showed up. He's one of the main architects of WASM. And he said, well, of course WASM has those safety properties. It was designed to have those safety properties. So one of the main WASM designers had designed it to have those safety properties, but just like I have failed to communicate to the general community these strong safety properties that we've gotten into JavaScript, Andreas at that point had apparently failed to communicate it because nobody else in the big WASM standards meeting, in the absence of Andreas in the room, knew that it was intentional.
Okay, so C code written to WASM will have the safety properties.
So
I would try Rust instead.
Hold on, that's going on. So having raised WASM and made a statement about safety properties, I need to make some distinctions here. The WASM we have now is one in which a WASM instance, or WASM module instance, as they call it, is one that has a flat linear address space of data, and also something called the anyfunc table, which you can think of as a flat linear address space of capabilities. Let's not worry too much about what capabilities means in this context. Because WASM can be a faithful target of C compilation, it must therefore have all of the safety properties of C, i.e. none. Because otherwise it wouldn't be a faithful target of compilation.
Yep.
So the sense in which WASM is a capability machine currently is in the sense in which an operating system can be a capability machine, which is the separation of one address space from another and how code in one address space can interact with code in another address space. The linkage between module instances that don't share memory and don't share the anyfunc table is an interaction only by invoking functions that were exported by one and imported to the other. And therefore, the interaction is only according to the behavior of the invoked function. And the separation there is, as far as I can tell, flawless, but it doesn't have the expressiveness properties because you can't pass capabilities over the invocations of capabilities currently. Further proposals repair the expressiveness shortfall, in particular, a later proposal from Andreas called reference types. Repair the expressiveness problem while still leaving the granularity being a process-like granularity. A later proposal from Andreas called WASM-GC introduces managed objects, introduces fine-grained, typed, encapsulated objects with opaque, unforgeable references between them. And at that point, you have now a fine-grained object granularity capability machine. In particular, if you use WASM-GC while contracting the size of the linear address spaces to 0 so that all the state is in the managed objects, you actually do have an object capability machine. And I asked Andreas, and he confirmed that that was the case.
Okay, in other words, you got rid of pointer arithmetic.
Yes.
Yeah. So I note that that sounds like a very good state to be in, specifically in the way that you've previously mentioned the notion that a lot of code is just transforming an input to an output, and therefore it does not need it doesn't need state that sticks around, and the worst that can happen is that the output is wrong, and so this can be true of if you have tiny address spaces then that you throw away when you're done.
Right.
Then you are limiting attack.
That's right.
In that way.
Right. So WASM also gives us a way to take old C code.
Yes, exactly.
That doesn't need much authority and run it safely within a confined compartment such that JavaScript code, as well as other WASM code, can safely make use of it. And without using an OS process boundary as a barrier. You have the domain crossing, the crossing between between mutually suspicious protection domains has the overhead of a function call. So this is really quite wonderful. You've got a operating system like security in the crossing between address spaces at with the speed of essentially a function call.
Yeah, so is this Andreas WASM guy involved in TC39? Because he's clearly doing OCAPy security things, right?
So
sounds like there's two parties not communicating.
So Andreas has been for a very long time heavily involved in TC39. He was one of the major engineers on V8. He repeatedly tried major ambitious efforts to clean up JavaScript, not primarily targeted at security or OCAPs, primarily targeted at sound static typing. And those experiments were very ambitious, but did not succeed.
Did not succeed technically or did not get adopted?
Did not succeed. It's sort of a mixture.
Okay.
It did not succeed technically at creating something that was a plausibly adoptable thing. And it was sufficiently far from plausibility that there was no attempt to push them forward to adoption. It's not that it failed an actual adoption experiment. So in any case, then when WASM started happening, Andreas rapidly shifted his attention to WASM. Andreas has now left Google and joined Dfinity, a blockchain startup, which is focused on WASM as part of a decentralized, replicated object capability fabric for doing smart contracting. And at Dfinity, as far as I know, I feel pretty confident saying that Andreas no longer has any significant involvement on the JavaScript side. He's focused on WASM.
Is that spelled R-A-Z-M?
No, RASM.
R-A-S-M.
It's short for WebAssembly, WASM.
It's WASM.
I'm sorry, what did I say?
You said W?
Oh,
WASM.
It's WebAssembly. It's an assembly language
Okay.
for the web.
Okay, so now I've finished the intro to the talk. Let's get to the meat of it. So
You're right on time.
yeah, so let's take a look at the anatomy of an exfiltration and an exfiltration in the kinds of frameworks we're talking about. And I'm trying to lay out this anatomy in an abstract enough way that it covers all four of the cases we just went through. So first of all, there's something that's holding a secret, but holding it in a leaky manner. And
you can have you can have the you could have the holder of the secret which is interacting correctly and overtly with something else it doesn't consider to be malicious, but
right now I'm trying to stay abstract enough that it's covering all those cases. So at this point, just consider this to be a framework for talking about particulars.
I suspect still have a complaint, but carry on.
Listen for the rest of the categories.
Okay. Yeah, and so then the secrets are carried over some internal channel such that code that's local enough to read the channel or to hear the channel or to
Sense the channel.
To sense the channel can sense the information that's being leaked over that channel. Often, that adversarial code, in order to sense the information on the channel, must have access to some way to sense the duration of time. The Timers, Fantastic or Not, refers to this wonderful paper called Fantastic Timers and Where to Find Them, that points out that even if you suppress everything that's explicitly labeled as a timing channel or thought to be a timing channel in the browser, the other forms of non-determinism in the browser can be leveraged to provide the ability to sense the duration of time, and in fact, quite surprisingly, to quite an alarming degree. The granularity of time that you're able to measure accurately using some of these timers were quite surprising. And then the local spy, having gained the secret, then has to find a way to leak the secret over an external channel in order to get the secret to the bad guy, to the lair of the bad guy that can then make use of the secret. So that's sort of the overall anatomy of the exfiltrations that cover all these cases.
So if there is no spy in the machine, then you're not counting that as exfiltration?
If there are exfiltration cases that are interesting and dangerous that don't fall into this anatomy.
Okay. Okay. And my meta feedback is I think you need lines on this chart.
Make it a DAG.
So now let's take a look at some cases in terms of this taxonomy. So in terms of the security boundaries, according to the official advice, there's the coarse grain boundaries, the origin boundaries that browser makers or some browser makers are now trying to map to process boundaries. Process boundaries are certainly much more defensible through well-understood defenses, address space separation as well, as you know. But the coarse grain leakage that people are recommending, the coarse grain leakage that people are bringing attention to is leakage between leakage between pages, leakage between origins, where the adversary is assumed to simply be, let's say, another tab of the browser that has visited the adversary's site. So you can have a tab that visits pages you don't trust. People do that all the time. It's expected that people do that all the time. This is one where people don't have any illusions that people only visit sites that are trustworthy.
Does this also apply to iframes?
It does. People use iframes in separate origins in order to have the iframe visit sites that the containing frame does not trust, and that remains part of what is considered to be
good practice
within the recommended practices by the official security advice. That if it's an origin boundary, it's supposed to be a protected boundary. So in this case, the browser actually does a fairly good job of protecting leakage between origins over overt channels, and the dangers are the non-overt channels. And since the dangers are the non-overt channels, the access to some kind of timing is essential. And that's sort of the canonical form of leakage that you're supposed to pay attention to according to the official advice. And then there's the fine-grained boundaries, which is the leakage of code within an origin, code that is linked together, in which case the leakage is often by reachable objects. The internal channel, given that objects are not protected from each other, so things like the prototype poisoning that Brendan called attention to of replacing function.prototype.apply, being linked together in JavaScript as it is means that everything can corrupt everything else. So that enables uncontrolled internal channels through objects, to objects that are reachable. Bad code that's linked in, libraries, plugins, mashups can be the spy. Timers, in this case, can be helpful, but they're certainly not required. There's plenty of opportunities, even without making use of non-determinism or timers, because you have the possibility of overt corruption. And then, once again, the normal technique to get the stuff off of the machine and to the bad guy's lair is an overt communications channel over the web, like an XHR. So now let's take a look at the mitigations. So now the column on the left is the hazard, is the danger we're trying to mitigate, and which is the work of the black hats. And the column on the right are the mitigations that we're trying to apply, which is the job of the white hats. So in order to address the leaky secrets, people are trying to code constant time cryptographic algorithms, and as the quoted research paper shows, this doesn't work. With regard to the internal channels, what Meltdown and Spectre have made clear is that the speculative execution of processors, which the processor manufacturers did because it gives them a significant speed up in execution, that people are now looking for ways to dampen down the speculation, and they're running into very expensive trade-offs in that trying to find what speculation can they suppress that has a big benefit in mitigating the channel without having a big performance hit. And that's a difficult exploration, and it's good that people are exploring it, but that's what's going on there. The origin separation is what is being recommended as the way to overcome Meltdown and Spectre as they try to mitigate the cross-origin leakage while they've essentially given up on the intra-origin leakage, the leakage within an origin. They're trying to say separations of origins become separation of processes in the browser. And then they're trying to mitigate Meltdown and Spectre in such a way as to practically prevent leakage between processes. But I've asked, and nobody has an abstract argument from first principles that their mitigations have even limited the bandwidth to an upper bound that they can derive from first principles. They're only judging the success of the mitigations by their success at constructing attacks. So it's
is it also the case? Is it also the case from the Princeton exposure that this is not relevant because that's libraries that you just incorporated and used, and so they're essentially same origin, right?
So right. I mean, so I'm making 2 points here. One is that even if you follow the official advice and even if it was possible to follow assuming it was possible to follow the official advice and you followed it, that the leakage of secrets by Meltdown Inspector across origins in the browser, which are even when mapped to process boundaries, we don't actually know how leaky it is because no one has been able to derive from abstract arguments without looking at particular attacks an upper bound on the leakage. And I know this from having asked people who are working on that. The immediate thing that the browser makers did in reaction to Meltdown Inspector is they turned off some especially egregious high-resolution timers, so something called shared array buffers, which gave access to very, very high-resolution accurate time by essentially having multiple threads communicate through shared memory. One thread can just say, do a tight loop incrementing, and the other thread can...
Now you have a timer.
Now you have a timer, that's right.
It's got problems, but it's good enough.
Right. So people turn that off. There's also approaches like JavaScript 0, which is a particular mitigations at the JavaScript level to try to reduce timing information. But these measures are temporary and understood to be ineffective long-term. We need long-term timers will be available. One will be able to derive high resolution timing information from them, and we need solutions long-term that are not incompatible with that. And that, again, is the position of the people working on this. At the level where the adversary is malicious code on a separate tab in the browser that has visited a malicious site, that adversary necessarily has access to overt channels, the ability to communicate back to its site of origin. So there's no path for shutting off the external channel when the adversary is simply a page from a malicious site. So these mitigations together sometimes foil the attempt to leak the relevant secrets back to the adversary, but nobody can say when the adversary is actually foiled because nobody has an abstract argument. So we're trying to mitigate. It's good that people are trying to mitigate this, but nobody can make strong statements at any point about how mitigated we are. So nobody knows how safe their secrets are, even when all of these mitigations are applied. Okay, let's take a look at the fine-grained leakage. And now we're talking about leakage among linked together code within an origin, within a web page. This is the subject, largely the subject of the four categories of attack that I've explained in the intro. So with regard to reachable objects, the realms give us the ability to separate subgraphs of reachable objects such that they're only put in contact with each other, able to interact with each other according to code that is written to protect them from each other. And in particular, realms give us this compartment scope that gives each separately linked piece of code a pseudo-global, an object that acts like their global scope, which is populated only by the powers that the code in that compartment needs. So this gives us a means to practice Pola rather directly with the compartment scope. Frozen realms further protects the primordials, which means that it freezes all of the objects that are implicitly shared by all code running in the same realm, all the objects that exist before code starts running. So that prevents the corruption by primordial poisoning. The modules key proposal, which is also a proposal in front of this committee, further enables module linkage of modules, which is now the preferred linkage mechanism that the language supports, enables POLA discipline to be applied on a per module basis. So individual modules can be denied access authority while still being linked with other modules. And timers, for fine-grained adversaries, we can deny them access to timers under some conditions. So that's the when possible. But we can deny them absolutely. And likewise, in this case,
meaning that you can just deny them, discover what breaks, decide whether to re-enable or not.
Yes, yes.
Or rewrite them in a way that doesn't need that feature.
Right. I mean, yeah, exactly. You can. So, for example, I'll give an example. We're currently looking at the moment library. Moment library is basically a library for doing date arithmetic and internationalized date rendering. There's one part of it which renders the current time, but it's a very tiny part of the overall value that's delivered by moment.
Yep.
So if you deny it access to the current time, it can still do all the date arithmetic and date rendering you want it to do, but just not do it with regard to ambient implicit access to the current time.
Right. And in fact, you can instantiate it in a container in which the current time function returns a constant value provided by the creator of the container. And you would probably never notice the difference because probably the only thing you're doing with that is running it once.
I often use it in tests, but if you replace that with a constant, it would be just fine.
Yeah, and also something with access to the current time can obtain the current time, talk to, and if given access to moment, can communicate the time it wants rendered to moment without moment having ambient access to it. That's the key thing.
Yeah.
I'd like to disagree with the claim that replacing it with a constant would be a one-time reading would be good enough for many cases. It would not be good enough for any single-page application or thing which is displaying real-time messages and wants to display, this message is 3 hours ago, and so on. That's just minor thing, and that application is clearly explicitly wants to work at the current time. Just don't think about just we just put out this web page and it's done.
That's right.
We found that using it as replacing it with an event counter is very often sufficient.
So it's a sequence.
It's a sequence.
Yeah, and we just found out that Cloudflare did a very similar thing with date. Anyways, going back, so we can deny timers under certain conditions, basically for libraries that don't need it, or for which we're willing to break the small fraction of functionality for which they do need it if we just want to use the remaining functionality. Likewise, many libraries don't need the ability to communicate on the network. They don't need to talk back to the origin. They don't need to do anything which would cause the browser to initiate network communication. So under those circumstances, we can just deny that. And that means that under those limited conditions, we can not only foil the bad guy in his foreign lair, prevent him from getting the secrets, but we can know that we have foiled him. So it's a limited circumstances where it's possible, but for those possible cases, we actually know that we have succeeded. So what is this when possible constraint? Let's take a look at, when it is possible.
So I want to argue with knowing that you've done so.
Okay. Modulo bugs in the mechanism, of course.
I'm not thinking of bugs in the mechanism. I'm thinking of delayed exfiltration, for instance. What I do is I do the observing of covert channels, and I do a bunch of stuff, and I steganographically hide something in the database that I expect you to publish the photo later.
Yes. Yes, I completely agree with that.
Okay. So that's a subliminal channel out from the spy in the machine.
Right.
That's right. And in the case of date, that's very clear. And there's that will often occur so the transformation library is something that so I'm calling attention to this particular class of libraries and doing a informal random sampling of prominent NPM libraries. I've corroborated without, not carefully, but just sort of informally, that a very, very large fraction of the libraries that people actually get from third parties are there to do transformational jobs. Parsers, compilers, pattern matchers, parser generators, pretty printers, linear algebra, constraint solvers, data arithmetic, geometry, image synthesis, collection classes, which has an asterisk because there's a qualifier I'll get to there, machine learning that has an asterisk because there's a qualifier. If one limited those to the principle of least authority, the explicit things that are part of the browser JavaScript environment that you would arrange to deny them are basically none of these things need access to XHR, the thing that enables, that causes external HTTP requests. None of them need access to the DOM, i.e. they don't need access to the user. They don't need to be able to cause rendering. They don't need to be able to receive user interface events. They don't need sockets because they don't need other kinds of access to the network in addition to the XHR. They don't need access to files, even if they're running in Node where direct access to files is available. They don't need the non-local control flow information that we talked about before that's granted in a normal JavaScript environment by error prototype stack. So there's this large variety of things that are part of the normal environment, and this entire category of transformational libraries, to first approximation, doesn't need them.
So you said files, you're talking about local store in the browser?
I'm talking about Electron.
A node. Oh,
I'm talking about Electron where there's direct access to the file system, as well as Node itself.
Right.
So these things could execute safely on Node or an Electron, and be denied access to files, even though it's part of the normal JavaScript environment to provide that access.
But yeah, local store and IndexedDB and stuff need to be denied as well.
Right.
Yes.
Right.
Yes. That should be added to this list.
Perhaps worker threads.
Yep.
Yeah. And so part of what I'm calling attention to is the contrast here between knowing the current date versus being able to do data arithmetic. Data arithmetic is safe. Knowing the current date and time is not safe. The qualifications with the asterisks are minor, but I'll mention them for completeness. Collection classes, some collection classes can make good use of weak references in order to avoid causing memory to be retained that the job of the collection class does not need them to retain. However, weak references necessarily leak side channel information and therefore potentially covert channel information. You're giving access to non-determinism through the garbage collector. You're enabling garbage collection to be visible. And a friendly collection class might hide the non-determinism internally to build a deterministic surface, or it might surface the non-determinism depending on the purpose of the collection class. So that's one that has to be managed. And then also machine learning, often for various algorithms like that, you want to use randomized algorithms. Randomized algorithms need some source of apparent randomness. The default source of randomness in the normal JavaScript environment is something called math.random, which in fact is primordial mutability that, because it's not strongly random or strongly pseudo-random, has been used as a vector for attacks of communication through the ability to advance the random seed in a way that lowers the entropy of guessing the next random number.
It's tied across boundaries. So the seed is shared across boundaries is the problem here.
Right. Right, and that's because it's primordial. If it was an object that you instantiated, where it was each instance had a separate seed, and then sharing the instantiated object would be fine. That would follow capability discipline perfectly well. It's the fact that math.random is provided in the primordials, which everybody has implicit access to.
Yeah.
Okay. So the overall message of the talk is, let's clean up our mess.
So civilization hangs in the balance here, basically.
Civilization, I really believe that. I mean, I really do believe it. And I believe that one of the things that has happened since I first became aware of these issues is that civilization has come to rest on the infrastructure that our industry has created. And the infrastructure that this committee, the TC39 committee, is responsible for is no small part of that. The pervasive insecurity of that infrastructure does put civilization at risk. Reducing those risks amplifies the benefits that infrastructure provides while lowering the risk to civilization. And we know how to reduce that risk substantially.
So why didn't you tell me this before I first started writing code?
On this point,
This is for fun.
in one of my talks, I noted that there are so many vulnerabilities on the web. It's amazing that it's useful at all. And my conclusion was there just aren't enough bad guys to take advantage of them.
That's probably correct.
Give it time.
Okay. These are the references that I kept mentioning during the talk. These are all the sources of the explicit quotes, plus relevant immediately relevant other pages. Obviously, there's many relevant things that I'm not citing here, but these are all good starting points.
And what are those? What is this series at Princeton? Is it lectures or papers or
papers?
What? Papers.
Papers posted on the, and they're all available on the web. It's called the No Boundary series, and they're excellent. I really recommend them. So that's the end of the talk itself, and
A miracle, you got through it all.
yeah.
So how does SES and I forget the smaller one, Tiny SES, et cetera, fit into this? I mean,
So Tiny SES I did not talk about at all. I wasn't intending this talk to touch on Tiny SES, but
those things affect the fine grain OCAP.
so this slide, I backed up to this slide. Frozen realms give us very direct support for creating an object capability version of JavaScript that is a sufficiently large subset of JavaScript that it runs a tremendous amount of old code. And both experience at Google and experience at Salesforce. Experience at Google with regard to ES5 era code, and experience at Salesforce with regard to modern JavaScript corroborates that under the restrictions of frozen realms, a tremendous amount of old code successfully runs compatibly. So using the mechanisms of realms and frozen realms, we're rebuilding the SES library as a very, very thin layer on top of frozen realms. Realms and frozen realms actually do all the heavy lifting. And then to use those mechanisms to deny even access to the date and math.random is something that becomes very easy, and SES takes that additional step of actually creating a safe environment in which you can know for these transformational libraries that you have completely denied them the ability to exfiltrate by those means. And therefore, with regard to all code which can be packaged as transformational libraries, both code that is currently already packaged that way, as well as for other things, if you can separate them into a transformational component and a non-transformational component, which you often can, the vetting burden on the transformational component is vastly reduced because it simply isn't given the authority it needs to engage in a very wide range of attack. The remaining vetting burden is still very hard, and I would still say in many ways, for many purposes, unrealistically hard, but it's substantially reduced compared to the completely unrealistic vetting burden that various parties are claiming people should practice.
And perhaps something like headless browsers could be interesting as a test environment. Offline, you can just say, here's my JavaScript, run it in this restricted environment and see if it fails.
Yeah. One of the things that's very nice about modern JavaScript is that modern JavaScript is statically scoped. modern JavaScript strict.
What's the boundary of modern and pre-modern or pre-Cambrian?
Okay, so really it's strict mode is statically scoped. So ES5 introduced strict mode, but you had to opt into it by saying, I want my code to be in strict mode. Starting in ES6, a module for the concept of modules as a directly supported concept came in, and now finally so ES6 was 2015. Today, a tremendous amount of code has moved over to being expressed in modules.
And modules require strict.
Yeah, modules are strict by default.
Right.
Are implicitly strict.
Right.
They have no option to be sloppy. Strict code, you can statically analyze it for free variable references, so you can know every name that it's trying to dereference through the global scope. There's you can tell. You first of all have to see whether it's accessing the global object, which you can also tell statically. If it accesses the global object, for completeness, I need to say, if it's accessing the global object, then it can use reflection to gain access to global variables from the global object without mentioning those names. But in the absence of using the global object or letting the global object escape into code that you don't understand, you can only get access to global variables, which are the powers provided by the host, by mentioning their names.
Right.
And then there's modules import each other, which is the mechanism by which they link to each other. So the module keys proposal before the committee gives us the ability to control the access to authority through module linkage, to be able to say that certain modules can only import other modules according to certain topological constraints. So
What's the syntax for expressing that?
it's not a syntax, it's an API.
Oh,
And I'll just refer you to the proposal. There's nothing particularly insightful about, there's nothing surprising about the API. So in any case, between the realms proposal, the frozen realms proposal, and the module keys proposal, we have all the direct support. We will have all the direct support we need from the platform to do all of this, and with some overhead, but today a surprisingly small amount of overhead due to a large engineering effort, primarily by Salesforce. We now have shims for the essential mechanisms here, which run, shims being code that runs today that emulates the crucial parts of future standards. So you can now do this today using those shims. And for the shim for doing this with modern JavaScript is in progress, but it's going very well. And that means that this becomes a set of practical recommendations for use of modern JavaScript with fine-grained polydiscipline according to object capability practice.
Are these shims trustworthy?
The week of the 18th, we're going to do a week-long security review of the current shim code and how trustworthy we should regard it is something that we will be prepared to talk about, or rather, what the road is to trustworthiness.
Okay.
Is because we already know, based both on the Salesforce experience, our own testing, and the SES experience from Kahal, we already know that this is a securable way to go about things. And how far we are from arriving to a point where we're willing to recommend this for secure use, we'll understand soon.
I mean, for syntactic use and for sanity of the programmer use, if the programmer is being friendly, it doesn't have to be completely trustworthy.
Yeah. And with regard to, because the other thing is, we're not recommending that people don't use coarse-grained protection, that people don't protect things with process boundaries when they can. They absolutely should. process boundaries are a good security boundary, and when they're feasible for your problem, you should use them. However, much code for its functionality needs to be linked together. Nobody would reasonably try to put a process boundary between many libraries that one directly uses by Object API. So even if these mechanisms are far from trustworthy, you use them in addition as defense in depth to achieve defense where currently you're completely defenseless. And then as the mechanisms become stronger, the degree to which they provide further protections becomes stronger.
Well, thank you, Mark.
You're welcome.
So the one way I like to phrase this is,
Have we stopped recording?
No, you are now on screen. That's
Okay. Okay, go ahead.
I was going to say, the way I like to explain this to people is, I don't want to have to figure out every possible way an attacker could exploit my code. So I'm going to assume that the attacker takes full control over some unit. And my goal is to limit the damage that can be done.
That's right. This gives you much finer grained units.
That's right. That's
And,
exactly right.
and having some protection at a finer grain unit does not in any way negate the benefits that you had of whatever protection mechanisms you were applying to the coarse grain units that those fine grain units are within.
That's right.
That's my argument that you want OS as well as language.
That's right.
Now,
That's exactly right.
The point that Chip makes,
Let me make sure that was picked up on. What Bill said is why you want OS as well as language. Okay.
the point that Chip makes about that is that the result is you end up with more maintainable code. So if you're trying to build more maintainable code, you'll get security as a side effect. If you're trying to get more secure code, you'll get maintainability as a side effect.
Oh. Right, and this is the issue about abstraction frameworks, composition frameworks that help avoid the dangers of destructive interference, help both with regard to accidental destructive interference as well as intentional destructive interference. And a lot of what modularity, abstraction, software engineering is about is finding frameworks and patterns of composition that diminish the incidence and severity of destructive interference while gaining the benefits of composition.
So you have the holy trinity of reliability, security, and maintainability.
Yes.
And they all work together.
And they all work together.
Thanks. So civilization is safe.
Could be safe.
No.
It's savable. It's savable. It's unlike Zuko's triangle. You can have all three.
Yes. In fact, they come together as a package.
Yeah. Now, as far as civilization being safe, the only thing I'm prepared to say is that such matters help make things safer.
And we have lived as a species for a long time without perfect safety.
So the risk, there are a couple of movies that show what happens if the internet goes away. Dark Angel was a TV series, right? And Transcendence was another one that showed the consequences of
Also,
our reliance on the internet.
Also, Die Hard 4.
Which one was that?
I haven't seen that one yet.
That was the one with the fire sale.
Oh, yes.
Fire.
Oh yeah. And he like downloaded all the Social Security database or something.
All the financial information.
Yeah.
The Social Security computers.
Right.
And he was going to take all of the world's money.
Yeah.
Say something. Closing remark.
Closing remark. Well, let me just sort of go back to.
We're not your slides are
Thank you all for your time.
Okay.
Yes.
Thanks, guys.
So once again, reducing risks amplifies the benefits of the infrastructure that our industry has created. We know how to do that. We should take some responsibility for having put civilization in danger by having tempted it onto an infrastructure that people thought was much more secure than it was, now that we have succeeded at attempting civilization onto it, I think we should take some responsibility to clean up our mess.